Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel. Today's topic of discussion is software simulation and experimental verification of series parallel circuit properties. Today's lecture has three objectives. First, we'll use circuit theory to calculate expected values for a series parallel circuit. Second, we'll make use of circuit simulation software to simulate the same series parallel circuit. Finally, we'll verify both our calculations and simulation and build the series parallel circuit using real-world components and common electrical instrumentation. The intention of this 1-2-3 combo is to prove to you, yet again, that I am not some dim-witted peddler of nonsense, and the skills and theories I am presenting are real, demonstrable, useful, and most importantly, true. This lecture operates under the presumption you are marginally skilled in series parallel circuit analysis. At no time do I recommend resorting to a tedious battle of attrition by reducing and returning series parallel circuits to a single resistor equivalent, but rather I am recommending you make use of pure series and pure parallel properties and visualize series parallel circuits at the nodal level from the perspective of flowing current. If you are not familiar with this methodology, please take the time to check out the series parallel circuit properties and the voltage divider circuits lectures available at the Big Bad Tech channel. Additionally, for those of you unfamiliar with circuit simulation software, please take the time to check out the software simulation of series circuits and software simulation of parallel circuits lectures, also available at the Big Bad Tech channel. In addition to reviewing basic series and basic parallel circuit properties, these lectures perform a brief orientation to a generic circuit simulator, in this case National Instruments Multisim version 11. This lecture is meant to be a continuation of these two lectures, and as such I will operate under the assumption you can navigate your chosen circuit simulator's operating environment and can build and simulate a basic circuit. Our first task is to analyze a basic series parallel circuit consisting of a single source, a switch, and 4 resistors. In this case, E is a 16-volt source, R1 is a 2.2 kilo-ohm resistor, and R2, R3, and R4 are all 1 kilo-ohm resistors. Between the junction of R1 and R2 and R3, let's introduce an SPST, single pole, single throw switch called SW1. By all means, pause the lecture and solve for voltage across all components, including the switch, current through all components, and source current for 2 different situations. 1 when switch 1 is open, and 2 when switch 1 is closed. As a refresher of the advice I issued in the voltage divider circuit lecture, I must emphatically remind you that the closure of switch 1 makes this an entirely different circuit and must be approached as such. Absolutely none of the values you obtain during the analysis of switch 1 while it is open can be used to solve for any other quantity while it is closed. These are 2 totally different circuits, necessitating 2 totally different analyses. When switch 1 is open, this is in effect a pure series circuit consisting of solely R1 and R2 in a pure series relationship with the source. Current in a series circuit is the same, IS equals I1 plus I2. A KVL analysis of the closed series circuit suggests E equals V1 plus V2. No current can flow through the open switch 1, and no current will flow through R3 and R4. Therefore, I3 and I4 both equal 0 amps. With no current flowing through these 2 resistors, no voltage will be dropped across them. V3 and V4 both equal 0 volts. A KVL analysis of this loop suggests that E equals V1 plus the voltage across switch 1 plus V3 plus V4. An additional KVL analysis, accounting for polarity induced by conventional current, suggests that V2 equals the voltage across switch 1 plus V3 plus V4. Given V3 and V4 are both 0 volts, this suggests that the voltage drop across the open switch will be equal to the voltage drop across V2. I'll solve for V1 using the VDR. The VDR setup to solve for V1 is as follows. Substituting in the necessary values, we find V1 to be 11 volts. We can use KVL or another repetition of the VDR or Ohm's law to solve for V2. Our earlier KVL analysis suggests that E equals V1 plus V2. Substituting in the given value of E and the calculated value of V1 and solving for V2, we find V2 to be the remaining 5 volts. We can use Ohm's law to solve for the current through R2, where I2 equals V2 divided by R2. Substituting in the necessary values, we find I2 equals 5 milliamperes. Given the open switch 1 makes this a pure series circuit, we can use the most fundamental of series circuit properties to determine I1. I1 equals I2, which equals the source current, and they all equal 5 milliamperes. Given R2 experiences a 5-volt drop, it can be said that open switch 1 will also experience a 5-volt drop across its two terminals when open. No current will flow through the open switch, so I3 and I4 equals 0 milliamperes, and V3 and V4 will be 0 volts. This all changes when we close switch 1. Absolutely none of the assumptions or steps we made in our previous analysis are valid and must be tossed out with the trash. The closure of switch 1 makes this an entirely different series parallel circuit. We'll assume switch 1 is an ideal closed switch. It presents no opposition to flowing current. Therefore, voltage drop across its two terminals should be 0 volts in the closed state. Source current must flow through R1. Therefore, IS equals I1. Conventional current leaving the right end of R1 splits between two paths. The left branch travels through R2. Therefore, I left equals I2. And the right branch travels through both R3 and R4 in series. It can be said that I3 equals I4 since R3 and R4 are in series with one another. The current in the left branch, I2, plus current in the right branch, either I3 or I4, equals the incoming current I1 or IS. Since R2 is in parallel with the series combination of switch 1, R3, and R4, it can be said the voltage drop across these two paths from B to ground is the same, whether you travel from B to ground through resistor 2, or the switch in series with resistor 3 in series with resistor 4. This means E equals V1 plus V2, or E equals V1 plus the voltage across the closed switch plus V3 plus V4. A final KVL analysis of this loop suggests that V2 equals voltage across the closed switch plus V3 plus V4, accounting for the polarity induced by conventional current. This supports our initial assumption that voltage across the B to ground path is the same regardless of which path is traveled. Voltage across paths in parallel is the same. R3 and R4 and the ideal closed switch can be combined in series with one another into a simplification I'll call R prime, with a value of 2 kiloohms. R prime is clearly in parallel with R2, and making use of parallel circuit properties, we could say that V2 equals VR prime. R2 and R prime can be combined into a parallel simplification I'll call R double prime, with a value of approximately 666.7 ohms. R1 and R double prime are clearly in series with one another, and the most basic of series circuit analysis techniques can be used to solve for unknown quantities. Any further reduction of series parallel circuits beyond pure series or pure parallel circuits is an unnecessary waste of time. Let's start by using the VDR to solve for V1. The VDR setup to solve for V1 is as follows. Substituting in the necessary values, we find V1 equals approximately 12.28 volts. We can use Ohm's law to solve for the source current and current through R1. I1 equals V1 divided by R1. Substituting in the necessary values, we find I1 equals approximately 5.58 milliamperes. We can use KVL or another repetition of the VDR or Ohm's law to solve for VR double prime. My choice is KVL. The KVL analysis of this pure series circuit simplification suggests that E equals V1 plus VR double prime. Substituting in the given value of E, the calculated value of V1, and solving for VR double prime, we find VR double prime to be the remaining approximately 3.72 volts. Given R prime is in actuality the parallel combination of R2 and R single prime, we can say that V2 equals 3.72 volts and VR prime is 3.72 volts. Given R prime is the series combination of R3 and R4, and our understanding that VR prime equals V3 plus V4, we can use the VDR to solve for the voltage drop across R3 or R4. The VDR set up to solve for V3 is as follows. Notice the applied voltage for the series path of R3 and R4 is VR prime, not the source voltage. Substituting the necessary values, we find V3 equals approximately 1.86 volts. Using KVL or Ohm's law, we can solve for V4. Given VR prime equals V3 plus V4, we can substitute the calculated value of V3 and VR prime and solve for V4 to be 1.86 volts. Realize we needn't have been so circuitous in the analysis of V3 and V4. Since R3 and R4 are equal resistors in series with one another, they should drop equal amounts of voltage. 3.27 divided by 2 is 1.86 volts. We can now use Ohm's law to solve for I3, where I3 equals V3 divided by R3. Substituting in the necessary values, we find I3 to be 1.86 milliamperes. Given R3 is in series with R4, it can also be said that I4 is also equal to 1.86 milliamperes. Given our previous understanding that approximately 5.58 milliamperes of current entered node B, and the series elements within the R prime path are known to experience a current draw of 1.86 milliamperes, we can use Kirchhoff's current law to solve for the current through R2. If I1 equals I2 plus IR prime, we can substitute in the calculated value of I1 and IR prime. We can solve for I2, where I2 equals approximately 3.72 milliamperes. A quick check using Ohm's law should verify this calculation. If I2 equals V2 divided by R2, substituting the necessary values, we also find I2 to be 3.72 milliamperes. I've got a reasonable degree of confidence our analysis is correct, and we can proceed with part 2 of this exercise. Part 2 has us assemble this circuit in our circuit simulator of choice. Recall, my sincere advice when using circuit simulation software is to 1. Place all components and indicators on the blank workspace prior to wiring anything together, and 2. Incorporate ammeters and components in series first before placing voltmeters in parallel as a final step. Notice this time, however, I've just built the circuit with no indicators in place. If I needed to incorporate an ammeter after the fact, it would necessitate the tedious removal of a wire, the insertion of the ammeter, and then the reconnection of the circuit. This is a serious drag, and liberal use of measurement probes saves you these time-consuming steps. Notice I've incorporated 4 measurement probes inside our circuit. Probe 1 will read the source current traveling through R1 and will indicate the voltage at the top of R1 with reference to ground. Probe 2 will read the current traveling through R2 and will indicate the voltage at the junction of the bottom of R1, the top of R2, and the left terminal of switch 1 with reference to ground. When switch 1 is open, R1 and R2 will be perfectly in series with one another, and probe 2 should read the same current as probe 1. Probe 3 will read the current traveling through both R3 and R4, will indicate the voltage at the junction of the right terminal of switch 1 and the left terminal of R3 with reference to ground. Probe 4 should read the same current as probe 3 since they are in series with one another. The only new information probe 4 provides is the voltage at the junction of the right terminal of R3 and the top terminal of R4 with reference to ground. When switch 1 is closed, current through probe 2 plus probe 3 should equal the current through probe 1. When the circuit is simulated, the probes indicate values consistent with our first analysis when switch 1 is open. The current measured by probe 1 equals the current through probe 2 at 5 milliamperes, because with no other path, R1 and R2 are perfectly in series with one another. Probe 3 and probe 4 indicate no current and no voltage with respect to ground. The voltage at probe 1 is 16 volts higher than ground as can be expected. The voltage at probe 2 is 5 volts higher than ground as can be expected. This means V2 is 5 volts as expected. Additionally, this means V1 is probe 1 with reference to ground minus probe 2 with reference to ground, or 11 volts as expected. The voltage drop across the open switch 1 is the voltage of probe 2 with reference to ground minus the voltage of probe 3 with reference to ground, or 5 volts as anticipated. When switch 1 is closed, the circuit simulator probes indicate values consistent with our second analysis. The current measured by probe 1 equals 5.58 milliamperes. The current through probe 2 equals 3.72 milliamperes. With the closure of switch 1, R1 and R2 are no longer perfectly in series with one another. The missing 1.86 milliamperes of current is traveling through the right-hand path of R3 and R4 in series. Both probe 3 and probe 4 indicate 1.86 milliamperes of current. The voltage at probe 1 with reference to ground is 16 volts higher than ground, as can be expected. The voltage at probe 2 is 3.72 volts higher than ground, as can be expected. This means V2 is 3.72 volts as expected. Additionally, this means V1 is probe 1 with reference to ground minus probe 2 with reference to ground, or 12.28 volts as expected. The voltage drop across the closed switch 1 is the voltage of probe 2 with reference to ground minus the voltage of probe 2 with reference to ground, or 0 volts as anticipated. The voltage at probe 3 is 3.72 volts higher than ground, and the voltage at probe 4 is 1.86 volts higher than ground, as can be expected. This means V4 is 1.86 volts as expected. Additionally, this means V3 is probe 3 reference to ground minus probe 4 reference to ground, or 1.86 volts as expected. I'm reasonably confident we can proceed with part 3 of this exercise and build this circuit using real-world components and instrumentation. Let's start out by grabbing a 2.2 kilo-ohm and 3 1 kilo-ohm resistors from the component drawers and checking out their color codes and values. A 2.2 kilo-ohm resistor with 5% tolerance should have a 4-band color code of red, 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 gold. 1 kilo-ohm resistor with 5% tolerance is brown, black, red, gold. The ohm meter says R1, the 2.2 kilo-ohm resistor, is within spec. The ohm meter says R2, one of the 1 kilo-ohm resistors is in spec. The ohm meter says R3, one of the 1 kilo-ohm resistors is within spec. Finally, the ohm meter says R4, the last of the 1 kilo-ohm resistors, is within spec. This simple functions check assures no faulted components are unknowingly used to build a circuit. Additionally, it prevents a misreading of the 4-band color code from becoming a problem later. For example, if you happen to pull a 220 ohm resistor from a component bin marked 2.2 kilo-ohms, your first clue of a problem will be the brown third band. If this escaped your notice, an ohm meter indicates this resistor has a value of 0.22 kilo-ohms, or 220 ohms, clearly not the 2.2 kilo-ohm or 2200 ohm resistance you're looking for. Again, your understanding of engineering prefixes is a core skill and will be continually employed. We'll start by physically assembling the circuit on the proto board in a fashion almost identical to the schematic. Notice I've replaced switch 1 with 2 wires. If I wanted to close switch 1, I'd have to replace this with a single wire connecting these 2 nodes. Now let's set up the voltage source to supply 16 volts. Notice this is the voltage value in the unloaded condition. Now we can verify the output voltage in the loaded condition by supplying our circuit with current and readjust as necessary to ensure we're truly at 16 volts. Now with switch 1 in the open position, we can take voltage and current measurements. The DMM in voltmeter mode indicates V1 is very close to our anticipated value. The DMM in voltmeter mode indicates V2 is very close to our expected value. The DMM in voltmeter mode indicates the voltage across the open switch is very close to our anticipated value. An ammeter used to measure current in our pure series circuit indicates IS, I1, and I2 are very close to our anticipated value. Finally, an ammeter indicates R3 and R4 experience no flowing current when switch 1 is open. Now we can replace the open switch 1 with a single wire connecting the 2 nodes. Switch 1 is closed and we can now take voltage and current measurements. The DMM in voltmeter mode indicates V1 is close to our anticipated value. The DMM in voltmeter mode indicates V2 is close to our anticipated value. The DMM in voltmeter mode indicates the voltage drop across the closed switch is essentially 0 volts. The DMM in ammeter mode indicates our source current and I1 are very close to our anticipated value. The DMM in ammeter mode indicates the current through R2 only is very close to our anticipated value. The DMM in voltmeter mode indicates V3 is close to our anticipated value. The DMM in voltmeter mode indicates V4 is very close to our anticipated value. The DMM in ammeter mode indicates R3 and R4 are experiencing current very close to our expected value. The tasks we intended to accomplish are complete. First, we use circuit theory to calculate expected values. Second, we use a circuit simulator to simulate expected values. Finally, we built the circuit using real-world components and observed and verified our expectations. Let's close out this lecture with a brief bonus round discussion of troubleshooting scenarios. Very rarely will a lab go this smoothly, and it is incumbent upon you to develop troubleshooting skills that can get a lab headed south pointed back in the right direction. The most essential of troubleshooting skills is your understanding and application of basic electronics theory and how the circuit was intended to operate. You simply cannot troubleshoot a system if you have no idea how it works. Current through elements in a series path is the same. Voltage across paths in parallel is the same. For every rise there is a drop, and what goes in must come out. Even in troubleshooting scenarios, these properties will always hold true, and you must interpret any observations on faulted circuits with this in mind. First, let's start out with a circuit built with the wrong components. While you've busied yourself with performing pre-lab calculations, let's say your lazy lab partner experiences an a-characteristic burst of motivation and enthusiasm and has taken it upon themselves to build this circuit. However, they've not been disciplined enough to check the 4-band resistor color code or have applied it incorrectly. Additionally, they shortcutted the check of the components using the ohm meter. This hurried approach is equivalent to jumping out of a perfectly good airplane, having never once verified the chute you're wearing isn't in fact a backpack stuffed with old newspapers. Always check your gear before you commit. In this case, the as-built circuit, despite being structurally similar, is not the circuit you intend to build, and the only way you'd be aware of this is having performed the calculations in advance. While switch 1 is in the open condition, V1 is unusually low at approximately 2.9 volts, and V2 is unusually high at approximately 13.1 volts in comparison to your anticipated values of 11 volts and 5 volts. V1 plus V2 still equals the applied voltage of E at 16 volts. A quick check of the current in the purely series circuit indicates current is unusually high at approximately 13 milliamperes. This is not the circuit you're supposed to be working on. What gives? By all means, pause the lecture and figure out what's wrong with your lab partner's as-built circuit. The key to the resolution of this problem is as such. The instruments are not lying. Switch 1 really is open, and R2 and R2 are clearly in series with one another. The current through this circuit really is higher than expected, and the voltage drop across R1 and R2 really are respectively 2.9 volts and 13.1 volts. The solution to this troubleshooting scenario is well within the reach of individuals with an understanding of basic series properties and Ohm's law. At its core is the fundamental understanding that if current is too high, it's because resistance is too low. With switch 1 open, this is a pure series circuit, and the current through both resistors should be the same. Given we know the voltage drop across each resistor and the current through each resistor, a rearrangement of Ohm's law suggests R1 equals V1 divided by I1 and R2 equals V2 divided by I2. A quick check of the observed values for the as-built circuit suggests R1 has a resistance approximately 10 times less than the desired value of 2.2 kiloohms. No wonder current was so high. No wonder V1 was proportionately so low. No wonder V2 was proportionally so high. A quick check of the 4-band resistor color code would indicate a brown third band on resistor R1. A quick swat to the back of your lab partner's head and a supervised second visit to the stockroom to get a 2.2 kiloohm resistor with a 4-band color code of red, red, red gold should rectify the problem. Can you now see the benefits of one of those quiet and reserved lab partners that sits there like a stuffed animal the whole lab? Errors like this shouldn't happen. Good lab practices dictate you check your gear before you use it. Read the 4-band color code. Check each resistor with an ohm meter. Pick a good lab partner. Far more important than these simple recommended practices is your application of theory to this troubleshooting scenarios. Do the calculations first. Know what to expect. You can identify excursions and pinpoint the problem. Troubleshooting Scenario 2. Let's say your lab partner is getting a little aggressive jamming the correct components into a protoboard, and current suddenly ceases when switch 1 is in the open condition. An ammeter would indicate no current flow. Let's say a DMM in voltmeter mode indicates V1 is 0 volts, and V2 is observed to be 16 volts. These observations alone should be sufficient to resolve this troubleshooting scenario. However, an additional set of observations can be taken while switch 1 is closed. Let's say in the closed position, an ammeter used to measure source current observes 3.81 milliamperes. DMM in voltmeter mode indicates V1 is experiencing an 8.38 volt drop, V2 is experiencing a 7.62 volt drop, and V3 and V4 are both experiencing a 3.81 volt drop. What's the problem? By all means, pause the lecture and pinpoint the problem. Key to the resolution of this troubleshooting scenario is again your understanding of basic electrical theory. When switch 1 was open, current through a pure series circuit ceased. No voltage drop will be observed across elements carrying no current. However, given every voltage rise is accompanied by an equal and opposite voltage drop, all voltage will be dropped across an open. Additionally, using a voltmeter referenced to ground, both terminals of R1 would be at 16 volts when switch 1 is in the open position, and there would be no differential across it. These observations made while switch 1 is open support the conclusion that R2 has been opened. Observations made while switch 1 is closed additionally support the same conclusion that R2 has been opened. Current now flows when switch 1 is closed because there is a return path through R3 and R4. Source current is less than expected because an additional current carrying path through R2 has been removed. The voltage drop across the open R2 is equal to the summation of V3 and V4. Far more expedient than your comparison of all these observations with that of expected values is your spatial awareness and basic powers of observation. Look at the circuit. Opens are often visually identifiable with a burned open component or a severed or misplaced wire, or in this case, a lead that's been flexed one too many times and is simply snapped off. If you observe no current in a series path, it's because that path isn't open. Case closed. Before you even think about busting out an ammeter, a voltmeter, or doing another calculation, take half a millisecond to look at your series path and see if it's connected. Current cannot flow through an open. Voltage will be dropped across the open. Finally, troubleshooting scenario 3 is one in which the circuit functions as intended while switch 1 is in the open position. However, source current spikes to 7.3 milliamperes when switch 1 is closed. In the closed position, V1 is observed to be 16 volts, and V2, V3, and V4 are observed to be 0 volts. An ammeter used to check the current through R2, R3, and R4 indicate no current. What gives? In this case, an improperly placed switch is inadvertently shorting out R2 when it closes. If you observe too much current, it's because voltage is too high or resistance is too low. Shorted components remove elements from consideration. No voltage will be dropped across the shorted component. Because of the improper placement of switch 1 across R2, rather than making or breaking the connection with a series combination of R3 and R4, these resistors will not be connected to the original series circuit whether switch 1 is open or closed. Before you even think about busting out an ammeter, a voltmeter, or doing another calculation, again, take half a millisecond to look at your circuit to see if it's connected properly. Shorts are often visually identifiable with a misplaced component, a misplaced wire, an errant or extra wire, or improper use of a protoboard. Too much current will flow through a path with a short in it. No current will flow in a path with an open in it. Shorts and opens inside series parallel circuits will affect these circuits differently based upon the placement of the short or open within a particular series parallel circuit. Only our understanding of basic series and basic parallel properties as applied to a specific series parallel circuit and your knowledge of how that circuit was intended to operate can resolve a troubleshooting scenario. Do the calculations first. Have a basis of understanding from which to compare expectations and observations. Okay, that's it. I want you to now place your hand on top of the internet and repeat after me. I believe if I show up on time and well prepared, lab will not be a frustrating and confusing force march through thorn bushes. I believe I can put to practice my series parallel circuit analysis skills and resolve troubleshooting scenarios using basic theory and instrumentation. I believe these skills and theories as presented are real, demonstrable, useful, and most importantly, true. In conclusion, we first use circuit theory to calculate expected values for a series parallel circuit. Second, we made use of circuit simulation software to simulate the same series parallel circuit. Next, we verified both our calculations and simulation by building the series parallel circuit using real-world components and common electrical instrumentation. Finally, we introduced 3 common troubleshooting scenarios, one involving a wrong component, one involving an open component, and one involving an improperly placed switch that shorted out a component, and used basic circuit theory and instrumentation to pinpoint and identify the problem. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.